Hello guys, have you ever thought of creating an electric vehicle? What do you need for that? Well, it's all about energy conversion. If we have, for example, electrical energy, we have a battery which holds electrical energy inside, and we want that electrical energy to be converted into mechanical energy. For example, that would be our electric vehicle. What do we need for that? To be able to make that conversion. So this electrical energy can be changed into magnetic energy. It's a magnet. And this magnet has poles. North pole and south pole. So the electrical energy will convert to magnetic energy, and then it will be converted to mechanical energy. And how it's done in practice? The electrical energy, when we get it out of the battery, we'll send it using this wire. And this wire goes into a coil and back to battery. So the electrical current comes out of the battery, goes that way, and along that way it creates magnetic field. This magnetic fields creates along the way. And if we have a lot of wire in one place, that we have a lot of magnetic field concentrated. And if we put, for example, iron core inside, for example, a screw, so this screw will concentrate this magnetic field inside and will hold it inside, and the screw will become a magnet itself. It will become a magnet with poles. On one side there will be north pole, and the other side there would be a south pole. And depending on the direction of the current, we will have a south pole at the top, or we will have a north pole at the top. So that depends on the direction of the current that flows through this coil of wire. So, for example, if our current flows this way from plus to 0 over this wire, and we send it backward, not from top to bottom, but from bottom to top. How do we do that? Let's break this connection and we put it backwards this way. So the current will go this way, and then here, and then it goes upwards and returns to the 0. So in this case, the current will flow opposite the opposite direction. And if we had South Pole at the top, North Pole at the south, at the bottom, then with opposite direction we will have South Pole at the bottom and North Pole at the top. Depending on the direction of the current, we will have different poles at the top and at the bottom. North Pole or South Pole, South Pole or North Pole. Yeah, and we will see that in real life. I have a screw with the bolt on it, with a nut on it, and around it we have a coil of wire. That's usual wire that was taken from Ethernet cable. And why I have two of them? Because if we have cross section, the wider cross section we have, the more current it tolerates. We have also power source. It gives us 12 volts and maximum current would be 5 amperes. So you see this wire, it creates, generally speaking, it creates a short circuit because it's just a wire. It has no resistance almost at all. So the current that flows through this wire is really great. So we have this screw with the nut on it, just like here on our drawing, and we will give it a current. We'll put it here and here and connect it here. Now we will see what this current with this electrical energy will make with this screw. We have a permanent magnet. The screw will become magnet, as we see, North Pole and South Pole. It will become magnet when it gets electrical current. Electric current flows around this screw and makes it into a magnet, electromagnet. But this is the permanent magnet. Its magnetic field doesn't disappear, never disappears. So we want to see how this screw, when it becomes electromagnet, will influence this usual magnet. We'll put, it has poles, South Pole, North Pole, and we'll offer this screw the South Pole side, and we put the electric on, and you see the nut doesn't like south, it likes north. It attracts north. If we offer south to this nut, it doesn't like it. It likes north. It attracts north. And so the nut is southern. It is south because it attracts north. And the another side is the hat, and it will attract south, because the hat is north. It will attract south. as you can see. And if we offer north to it, it will not take it. It will attract south. North, no, doesn't like it. Attract south. So the hat is north and the nut is south at the moment. The hat is north. If we change the direction of the current flow to the opposite, remember that the hat is north, and now what will happen? The hat is north, so will it attract north? Will it attract north? Yes, it will, because it is not north anymore, it's south. If we offer south to it, it will not accept it. It attracts north, because this hat was north before and now it is south. And here we have north. How do we know that? We will offer north to it. You see, it doesn't like it. It pushes it away. But if we offer south to it, yeah, it attracts the south. So as we can see in practice, just like on this drawing, the north and the south, if we send electric current into the coil, this coil will create magnetic field, which will reside in this core, metal core, iron core, and in our example it is screw with the nut, and this screw will become electromagnet, and the poles on this magnet, where will it have north, at which side it will have south, all depends on the direction of this current. Is it going from end to beginning, or is it going from beginning to end? So but yeah, now we see how to convert electrical current into mechanical energy. But we don't need this such useless mechanical energy. We want that it would, for example, bring us from one place to another place. We want it to be, to be able to drive our electric vehicle, and for that humankind uses such thing as a motor, and the motor, I have disassembled one, and made it very simple. I've deleted extra parts. So we have this casing. It is like a drum, and we have this inside of it, and on the walls, in the wall, we have these magnets, the same like this, and they facing the center with their faces, and these faces are of different polarity. They are they going in that they go in that succession, that if we have north here, north pole, then the next magnet is south, and the next is north, the next is south. So they facing with different each next magnet has different polarity facing the center. So if we and also we have a central part of the motor here, and it consists of heavy metal core, which consists of a lot of such discs or rings, and we have these spikes all around. These spikes, 1, 2, 3, 4, 5. Each one had a coil of wire, and I have left just 3 of these spikes with coils. It is just one wire, single wire, which surrounds the first spike, then goes to the second and the third, and it comes from here, Y1, this big wire. It comes here, and then it goes here, and it goes around this spike, just like this. This arrow shows the direction of this wire in this coil, and then when it's finished, then goes to the next spike, and it forms another coil with the direction opposite to the first one. It goes just like this on the second spike, and the third, and then it goes to the third spike and forms a coil of wire just like the first one in the same direction. So the second coil is of different direction comparing to first and the third. The first and the third coil are the same direction. The wire is wound here. Why it is important? Because if we give current here, electrical current, Y1 gives current here, the current goes here, then, for example, it moves around and creates magnetic field, and it creates one pole here, for example, north. And since the next coil is wound in opposite direction, then if we have north here, we will have south here, and we'll have north here. But if we have south here, then we'll have north here, and we will have south here. So that's because of the direction of this wiring is different at the first and the first and the third is, for example, from left to right, and the second from right to left. But it is just single wire is wound around the first spike, then the second spike, and the third spike, and then it goes back to the Y2, and goes back to the power source. So yeah, why do we need these magnets in that sequence? Why do we need, for example, if we have north here, why do we need south here and north here? It's just because if I will draw it on the screen. If we have all right, let it be power source, and we have a motor here, and the central part has 3 coils of wire. So when we give electric current here, and for example, the first coil will be north, the second is south, and the third is north. And around, all along the wall of this drum, we have magnets, with these magnets. And they are, for example, north, blue magnet, then red magnet, or south, then again north. And how will they react if these spikes, if these coils would become magnets? Well, north will push away the north. It doesn't want north. It's not its own. And the south, the next magnet, will push away the south. And the north will push away the north. But the next magnet, for example, south, if we have north, south, north, and then go south, it will attract this coil, because this coil is north. And south will attract north, north will attract south. So we have, if we have this central part of the motor, if it's placed this way, like, I'll put this cover. So if we have these coils, for example, here, and the first coil will become north. For example, we will put like this. The first coil will become north, the second coil south, the third is north. Then this northern magnet will push away this coil. But the next magnet, it is south, it will attract this first coil because it's north. And the second coil would become south because the first is north. It will be pushed away by the first magnet, but the second magnet will attract it because it's north. And the same picture with the coil number 3. So the force will be pushing from the backwards and attracting from the fourth, from the front, from the next magnet. And that's why this motor will move. This central part of the motor will move because of this magnetic force that will push away from the back and drive it to the next magnet. And when these coils will reach their own magnets, which their matching magnets, then they will stop because they have found what they were attracted to. And but before they stop, they will move a little bit further to the opposite to the magnets that they don't like, to the next magnets. So north will move a little bit to the north side. Why? Because of the inertia, force of the inertia. It will drive a motor a little bit further than it wants to be. Then it will come back to the best position when north facing south, south facing north, and north facing south. We will see if we give electric current to to this wire Y1, and we'll take it back to power supply from the wire Y2. And we'll hold this central part of the motor that it would not move, that it would that this motion wouldn't be too shaky. So now we leave it like this, and we hope that the first coil would become north, then it will be pushed away from the back to the front. Let's see. Yeah, like you have seen, the first has become north, and it was attracted by the south pole. So it was just like this. I'll show it once again. Yeah, as you can see, this motor jumped ahead. And now we have the matching magnets against these coils. North facing south, south facing north, north facing south. It's really nice picture. But the motor is not moving anymore. And if we want it to keep moving, then we must make sure that these magnets don't like these coils. And each given moment, all the time, they don't like these coils. And they will keep pushing it to the next ones. And when these coils will jump, for example, we give will now give current to these coils, and they will become magnets, north, south, north, and they will be pushed further by these magnets. Yeah, just like this. But you haven't seen, it was very quickly, and it was so that when they were pushed ahead, they a little bit went further than needed. They a little bit went to the magnets that they don't like. The north comes a little bit at the border, to the border of north, and when this happens, and in this exact moment, if we send the current to the opposite direction, not from Y1 to Y2, but from Y2 to Y1, then these poles of these electromagnets, of these coils, then will become opposite. For example, if it is north, it will become south, this coil. This coil will become north, and this coil will become south. If we change the direction of the current in that exact moment, when by the force of the inertia they have crossed this border a little bit, these coils, and before they return to the desired magnets, if we change the polarity of this current, if they change the direction of this current in this moment, then what will happen, they will not go back to their desired magnets, because they are not desired anymore, because this will become south, and this will become north, and this will become south, and they will be pushed away by these magnets further to the next matching magnets, to the opposite magnets. If this coil is north, it would be attracted by the southern magnet. But since it was supposed to be attracted, and it would come back to it. The north would come back to south, but it will not, because it's not north anymore. If we change the direction of the current, it will become south, and it will be pushed further ahead. And if we keep changing the current, the direction of the current in the right moment, just when this crosses the that's just this, when these coils cross the border of the desired magnets with undesired ones by the force of the inertia, then this motor will keep spinning. And how do we turn this? Well, I'll show you how it looks if we do it by hand. So we'll leave it like before. Suppose that the first coil will become north. We'll leave it like this, and it will move. If we leave it like this, it will move when we give current. As you can see, it has moved here and returned back here. And suppose we change the current when it reaches this hole. When it reaches this hole, almost, then we will change the current. We will swap these wires. The direction, we will change the direction of the current. We'll swap these wires and we'll see what happens. So we have this exact moment when these coils have crossed this border, just like this, and haven't returned yet to the desired magnets. And now we will make it south. We'll make this coil south. Yeah, just like you see, it went further because this magnet doesn't like it anymore. This coil became south. It's not north anymore. And the next coil has accepted it gladly because it is south. If we would have made it into north, it would go further this way. But how can we do it quickly? How can we change the direction of the current so quickly that it would match exact moment when the coil crosses the border with undesired magnet to be desired by it? By hand we cannot do that because we need to act too fast. But for our help, we have such thing as a controller. This controller is here we have it at Mega port D 0123. So this I'll take it a little bit smaller. Yeah. We have controller here. What is it? It's like a little computer. It has legs, a lot of legs, and these legs can be, no, most of them can be programmed to be either output or input. If it becomes input, then it starts to listen. It starts to listen for the state. The state can be 1 or 0. And this port will start to listen if it's input. Is it 1 or 0 on this wire that is connected to it? If the port we assign it to be output, then it will give out 1 or 0, whichever we wish to send, we will send to it 1 or 0. And almost all the legs here, like you see here we have PC6, PD0, so this is a port D, stands for port D, PD, PD1, PD2, so we have almost all programmable legs that can be either input or output, that will listen to signal or give out signal. In volts, that means about 5 volts. 5 volts, that means 1, 0 volts, that means 0. That's digital logic. And why do we need that? We need to inform our muscles. These are muscles that are connected to the motor. So we have these wires, 2 wires, just like we saw before, Y1 and Y2. Yeah, there. Here we have them labeled. So these muscles will send 12 volts to the motor at desired direction. So they can send, for example, we have 12 volts here, it comes here, downwards, and where does it go next? If we send 1, for example, here, we have 1 here, then this relay, that's a relay, it will act, this diode will flash, and the bridge will be closed. That means that we have path for the current, for the 12 volts, to go through this bridge, and then where will it go? Actually, it will go, it has no choice, it will go to the Y2, it will go here, it will come here back from the motor, and next we must close this bridge for it to be able to escape. This current comes back from Y1 and goes to the ground. It must have this complete path to the ground from 12 volts. So it's but how do we if we have 1 here, we have open connection here. If we have, and here to be opened, this relay must accept 1 and this wire, that's PD2 and PD1. PD1 and PD2 must be 1. That's they are in output mode and they have 1 at the same time. In that case, we would have electricity flowing from Y2 to Y back to Y1. Back to Y1. Yeah. But if we want to send electricity not to this direction in the motor, but to the opposite direction, not from here to here, but from here to here, what do we need? We need to change, we need to open different bridges. This one and this one. The 12 volts will go not here, it's closed already. The 12 volts goes here because the path is open here, and then it goes to the, it has no choice, it goes here, and goes here, and goes here along Y1, and then it goes here, and it goes here, and it goes here, and since we have made open this bridge, then it goes back to the battery, to the ground. That's how we change the direction of this current in the motor, and we'll have different polarities: north, south, north, south, north, south, depending on the direction of the current. And this controller can, but to open them we will need to have one nut here. We don't need to open them, but not at PD1, PD2, but at PD0 and here and PD3. So the controller is able to make these changes very quickly, to make PD1, PD2 in state 1, to put them in state 1, to send one at the PD1, PD2, or to send one at the PD0, PD3. And it can be timed exactly if we send one here and one here, then it's first and the last, then Y2 will become source, Y2 will become source, and Y1 will become drain. From here to here will go current. And if we send here to, if we send here and here one to these relays, then Y1 will become source and Y2 will become drain. To that, the current will go to the opposite direction all the time. And so this port D is set as output. That's our port D. Like you see, it says PD. That's port D. 0, 1, 2, 3. That's what we use. They are connected with relays, and these relays already send for us 12 volts to motor selected in a chosen direction, from Y1 to Y2 or from Y2 to Y1, depending on the where we have ones, where we have zeros at these 4 pins. Yeah, so this sets direction of the port D to the output, and then it sends the first leg and the last leg to 1, then delay comes, then all legs are closed. When these coils are already started moving, then we will wait a little bit and then we'll close the relays that the current would not go at all to the motor, and then we will send in opposite. We will send 1 to legs 2, and we will send 1 to these legs 1 and 2 to these relays, and then the current will go to the in opposite direction from, if it was from RL3 to RL0, RL3 to RL0, then this will go from RL1 to RL2, RL1 to RL2. So RL3 sends here, RL0 accepts it, and RL1 sends here, RL2 accepts it. So it comes opposite way all the time. The current swaps direction, and then the code goes to the first command from here. And we have delays, so they are set here in exact this timing is set exactly so that these coils would be magnetized to be undesirable by the previous magnets. These magnets under these coils will push them away all the time to the next magnets. Next magnets will attract them until these coils would change once again their polarity. They are all the time pushed away. And that's what our controller does. Ones and zeros here to the muscles, and these muscles already give 12 volts. This controller, it works from 5 volts, and it's pretty weak. It cannot handle this motor. It sends signals to muscles and this or relays, and they will handle this current that motor needs. They will send 12 volts to motor and take it back the current. So we have a controller, relays, four of them, and a little regulator, that's 5 volts regulator to feed the controller. It's 5 volts regulator to feed the controller. And so this pulse, this we can name this inverter. It takes direct current and gives from these pins, it gives alternating current. So we will give to this board 12 volts, and then we will here Y1, Y2, then we will place it like the first coil would become north, maybe, suppose, and we will hold this motor from shaking. So we will fire. Yeah, as you can see that yeah, you see it moves nicely. That's how they invented the first car. Joking. Now what we can see that we successfully converted electrical energy into mechanical energy that can be useful, but as you see we have two problems here, that this motor is way too weak and this motion is very shaky. And how do we fix that? Let's take a look at, yeah, as you can see, this our motor. Inside we have 3 coils which become electromagnets and end up and being pushed away all the time from these permanent magnets. They don't like these coils because they are of the same polarity. They push them away all the time, and the motor moves around. So if we give current to the coils just like this, they will become north, south, north, and they are pushed away. Like you see, the previous magnet doesn't like this, north doesn't like north, but south attracts this north, and that's why this motor moves ahead to the next group of set of magnets which attracts them until we change the polarity, we change the direction of the current. So they just like moving here, and then we will change the polarity or direction of the current, not from here to here but from here to here. So it was north, south, north. Now it becomes south, north, south, just like this. And now these magnets don't like them. Once again, this south pushes away the south because the south wants north, not south. They're being pushed away further. And how do we increase the power of this motor? We can add coils just like this. As you can see, these coils in total there are 9 coils now, and if we connect them like if we have this current coming to the first coil, then to the second coil, to the third, and then we will send it not back to the power source but to the next group of coils, and then they will go to the third group of coils when they finished running around these coils, and then we will send maybe to the battery. In that case, we will have not one set of coils, which are 3, but we will have 9 coils, just like one. We will have 9 acting just like the same coil. Why? Because we have at each coil we have the same red magnet underneath, like you see. the second coil facing the north magnet, the third coil facing the red magnet. So what is important here, that all these three coils at each set are facing the same magnets all the time, and that's why they become just like one, and that's why we will have 3 times more power when we use 9 coils instead of 3. But how? But yeah, we can use them like this. We will name them, we will call them yellow group. We will really connect them just like this. Current comes here, goes to the second coil, to the third coil, to the third group of coils. They will become as one. And we will hide these wires, and we will add a second group of coils, 9 more coils, and we name this group green, and we connect the battery using the different wire. If we for example, this is our yellow group, and we will name this green group, and it will have green wire. The yellow wire, the green wire, these are phases. These are different connections, and in different time they will be, in different moment of time they will be energized. We have now 2 groups of coils, each one of 9, consists of 9 coils, and we'll have one more group of coils, 9 more coils. We'll differentiate them by color. This is blue group, this is our yellow group that we started with, this is a green group, and each group has its own input. The wire of the yellow group comes here to these 3 coils, then goes to the second 3 coils, then third 3 coils, and the yellow or the green group just the same. It has its own input, and the blue group has its own wire. They are connected, all these 9 coils, to each other. And why don't we have outputs? We have 3 inputs, why don't we have outputs? If we have 1 input and 1 output, that's our yellow group, 1/3 of the yellow group. It has 3 coils, not 9. The yellow group has 9 coils, 3 in each section, but we have 3 coils, only 3. That's 1/3 of the yellow group, but it doesn't matter. The same 2 wires, input and output, just 1 wire consisting of 9 coils. It's 1 wire consisting of 3 coils. We have input and output, 1 input and 1 output. So we have 1 input, yellow, but where is the output? We don't have it. 1 input, green, we don't have output. 1 input, blue, and we don't have output. Why? Because it's where the tricky part comes. The engineers have figured out how to make this motor much stronger, and at the same time keep only 3 wires. They have connected all the outputs of these colored groups. They have connected just like this, all these outputs together, and it doesn't come nowhere. It just connects all these groups. And for example, if we send current to the green, if we have like Y1 is like green, if it comes here, then it goes along the green wires and it comes to the end, and then it goes here to the common place. And where does it go next? It depends on which of these wires we connect with ground. At that moment, we have one more controller, which is designed for three wires, not two. That would be our yellow, green, and blue. But it doesn't have the ground part. It's yellow, green, and blue. For example, if we connect green, or for example, with plus 12 volts, then 12 volts comes here to the green, goes along these green coils, and to the common place where all these groups are connected at the output. And when it where does it go next? It depends on which of these. For example, green is connected to 12 volts, and which of these two, this or this, we connect to ground. If we connect blue, for example, to ground, then this current will go to the blue group, and it will go backwards, not from beginning of the blue to the end, but from the end of the blue to the beginning. And that's why it will energize in the opposite with the opposite polarity these blue coils. And it can be calculated when exactly and which phase, there are phases like wires named phases, which of this phase, blue, green, or yellow, we connect to which direction. For example, we can send current to green and take it to the ground from blue, or we can connect 12 volts to blue and connect green to ground. Then it will go to an opposite way. And we can connect yellow to 12 volts and take it back from blue, connecting blue to ground. Or whatever we wish, that we can connect them using these relays, just like we did before. But these relays, they are not like muscles, and we can send 12 volts to one of them, this or this, and we can so they will go to the motor, these 12 volts, from this wire, or this wire. Here, three phases we can choose to send our current to, and back where does this current goes back, by which phase. It depends on which of these three relays we connect to ground. And so we can send the current at which phase we wish to, and take it back from which phase we wish to. And depending on the ones and zeros that we will put at the port D, from PD0 to PD 1, 2, 3, 4, 5 to PD5. Yeah, that's what we will do. But how do we know when we send current to which phase? to be to match the magnets under the coils, so that the coil, each coil would be undesirable for this magnet, that it would push it further. We need, if we have current coming from green, for example, and coming into the motor, and out of the motor it comes from blue to the ground, so we have energized green and blue, but the yellow would stay idle. It will not be energized. In each moment we would have one of the group of coils, one color, idle, unenergized. We have only, at each moment of time, we will have only two groups of coils energized. That's anyway, that's powerful enough. If we have three coils here at each moment of time, which work, three coils, working coils, and here we have 18, 9 and 9, 18 working coils at each time. But how do we calculate this moment so that all these 18 coils would be undesirable by all these 18 magnets which sits under them? For that we need such thing like Hall sensor. They are implanted in these spikes. If this sensor feels that nearby comes the red, the south pole of the magnet, then it will indicate 1, it will output 1. If this sensor senses something else, it will output 0. So that if we have three of these sensors and they are all connected, we have three wires coming, extra wires coming out of this motor. They are from sensors, and plus we have 5 volts for them to feed and 0. 5 volts comes here, makes it work, and comes out. So we have 2 wires for feeding them, and we have 3 outputs of them, so they can tell us which magnet sits under them. Is it south or north? So we have this combination of ones and zeros on them, which indicates which are unique for every position. For 6 positions they are unique, and they will once again repeat itself, this succession from these 6 states. For example, I have a motor here which I haven't taken apart. This motor we'll put here. I have a motor here which is about the same like on the picture, with Hall sensors inside. So these sensors, they have 5 wires like this, and the first one is 5 volts, the last one is 0, so the 5 volts comes here to the motor, to the sensors to feed them, and comes back from orange wire. At the center we have 3 wires, they are outputs of these sensors, so the sensors can tell which magnet sits under it. And also we have phases. These phases, besides these sensors wires, we have phases, yellow, green and blue. just like yellow, green, and blue. Yeah, we'll see how these sensors work. If we connect these sensors to the inputs of this controller, we have assigned some legs like inputs, not like outputs, and it's hard to see this, what it shows. Well, I will tell you, it's 0, 1, 0. Now it's 0, 1, 1. Now it's 0, 0, 1. Now it's 0, 0, 0, 1. Now it's 0, 1, 0, and so on. So we have these states or fingerprints of these Hall sensors, which when you rotate the motor, they will change these lights, but with each 6 states, after 6 states, they will repeat this sequence, they will repeat itself. And by that, the controller would know exactly where we are, at which angle this motor is at the current moment. So by knowing the angle, we know which magnets sit under which coils. And that's why, according to this information, we can send we can turn on the right phases. For example, yellow is output, green is input, or blue is output, yellow is input, for example, and that's how we energize the right coils under the right magnets, above the right magnets, sorry. And we have table. Everyone knows that whole sensors table, and we'll take images, and as you can see, we have whole sensors here and their states, whole sensors, their states, whole sensors, their states, and according to their states, we have this Q1, Q1, Q2, Q2, Q3, Q3. This means yellow Q1, green Q2, and blue is Q3. That's input, that's output, that's input, that's output, that's input, that output. So we have this table, and it says where to combination of outputs depending on combination of these whole sensors pattern. And that's in the right moment we can send in the right direction the current to the motor, so that its coils, 18 coils, 9 coils for input, 9 coils for output, would be undesirable by the magnets that sit under them, that they would be pushed further. And by knowing the right moment, by having the much more power, we have, instead of 3 coils, we now have 18. We will have much better motion of the motor. We will see it. Oi, sorry. Oh. Turn it off. Started to move already. Now we'll connect 3 phases. We have sensors. It will give our position, current position of the core, current angle, and I will hold it with the pliers. I will start. So as you can see, it's already, I give it 12 volts in the right time, at the right coils. All these coils, 18 coils, are undesirable by the magnets that sits below them at each moment of time. That's why they all the time they're pushed away, pushed further by these magnets, and it's quite quiet. It's quiet motion, just stable motion without shaking, and that's what we need. That's what we have achieved. We converted electrical energy into useful mechanical energy. We can now put it to our electric scooter or to our hoverboard, this wheel, and we can drive. But do you know, we can make this wheel much more powerful by giving it more voltage. It's now 12 volts. If we give 30 volts, it becomes much more powerful. So if you have battery which gives 40 volts, that would be very nice. You will have the real electric vehicle. So the principle behind this board is the same like before, but you need to keep in mind one thing. When you build this one for yourself, you will need to keep in mind one thing, that this motor and this power source, they can be the same. This motor can be a power source. Why? Because the motor and generator are the same thing technically. And when this happens, that for example, we have throttle button, that when we press it, then we will send current to the motor and we will take it back from it to ground. But when we release, for example, this throttle button, then it's like a idle state, that we, for example, we have enough speed, we are moving at the sidewalk with pretty high speed, and we release this button. We don't need to keep that speed, we want to slowly slow down, and that's when we don't send anymore the current to the motor. That's where all our bridges are closed. They don't let the current through. And that's where this motor will give current itself, because it spins. It spins with a lot of the high speed that rotates, and it generates. It's a generator. It's power source. It generates us the current, and it will send it here to the relays. And that's why we need to get it out somehow from the motor. We will get it to the battery. That's why we put here this Schottky diodes, 6 of them. If we have current here, if current comes here, we will send it to the battery, back to the battery. To the plus of the battery, we will send plus of the generator, because this voltage of this motor will be a little bit higher than the voltage of the battery, and the battery will start to charge from the motor. That can happen, but if we don't place Schottky diodes here, then what would happen? The motor will generate the current. The current has nowhere to go, and the voltage will start to increase, and it will be, for example, 100 volts, and it will burn out our relay, and it will get itself a path to the battery, for example, but it will destroy our relay. We don't want it to happen. We want to give it the path to escape. We want to give this current from the generator a path out. That's why we place everywhere. Each relay is protected with this Schottky diode, so that we can let the current out of the motor, because this motor is not motor anymore. It is generator. It generates the current when we don't use it like as a motor. It has the current that has nowhere to go. Yeah, and we have main power switch. We have regulator for feeding the controller. We have a throttle button. Here, well, I have put ammeter here, just to watch how much current does it eat, this electric vehicle. I put main switch here and the throttle button. I'll show you. Turn it on. That's how it works. So yeah, it's a pretty good thing. And the best of all, it's very simple. It has a few parts, just like this on these schematics. And these parts are, as you could see, these are the models. Tested working configuration, battery, INR 21700, and so on. So that works very nice.